Hello everyone, I welcome you to the day 28 of the training. This is so far an explanation for the interview questions, and from today for the next 2-3 days we will be discussing on what type of technical interview questions that you should be learning, what type of things you need to research on the interview questions. So and also I will try to give some tips for resume building, and if you need any assistance in resume building you can always contact to me. I will have one-on-one session with you and then we can restructure the resume. There is no hard and fast rule for resume structure, it depends on each individual person. So things apart, today we will going to discuss interview questions, some of the most asked technical interview questions. But without any delay, let us dive into the today's session. So today's agenda is interview questions, and first most asked and important questions, let us see. First question: what are flip-flops and latches? As an electronics engineering student or electronics engineer that you are going to be, you should be knowing about digital circuit fundamentals. So in that digital circuits, you should be knowing about flip-flops and latches in the sequential elements. Why? Because entire digital circuit implementation or the design that you are developing on FPGA or ASIC chip, it depends on all the sequential elements and combinational elements. So at the end of the day, it compiles to only sequential or only compile only combinational or only digital circuits. And why? Because of digital circuits, because they are fast than analog and they are way more reliable than analog circuits, and they are easy to implement, but for larger circuits as well. But analog, we can't design complicated designs with analog. We do achieve the results, but analog is way more basic than digital. So in the digital circuits, flip-flops and latches should be known. Flip-flops are the sequential elements which depend on clocks, and latches do not rely on clock. That is the major difference that you can answer in the interview session. Clock signals, and flip-flops are edge triggered and latches are level triggered. That means for every clock edge of the cycle, the data you have acquired into the D or any flip-flop input, it is divided into samples at clock periods, at time clock periods. It is divided into samples and the data is processed in a sequence manner for every passage of the clock. But in the latches, it is level triggered. It relies on the level. So hence the clock is working, the data transmits into a circuit. So it's like more like open gate circuit, and this is like closed gate circuit. In the closed gate circuit means there will be a stoppage of that thing if the passage of the clock stops, and the clock stops, and your bits of data might be lost in between. So that is flip-flops. But mostly, instead of latches in the FPGA design, flip-flops are most preferred. So we don't want a clocks to be stopped, so we use only flip-flops than latches. Next question: why do you choose FPGA in your design? Okay, there are several reasons in choosing FPGA instead of microcontrollers, because if you have a larger complicated design and that requires more number of IOs, wide number of IOs are required, means that are to be connected with different set of peripherals like buttons, keys, and LCD, USB port, Ethernet port, HDMI cable, audio signal conversions, audio jacks, and also all other pin configuration like GPIO pins. So these kind of IOs are available on the motherboard of FPGA, and that is one reason. And another reason can be requirement in terms of thousands of pin configurations. There are wide range of FPGA chips which have more than thousands of pin configurations. So that might be another feasible task to make a prototype and implement that design into the real-time application of your project. So the other thing is large number of memory requirement with larger bandwidth. In the FPGAs, we have a good set of memory blocks with larger memory designs and with good number of bandwidth. This bandwidth represents to the data transmission into the FPGA chip and the process of large numbers of data. That itself is nothing but bandwidth. Bandwidth is ability to send a bigger number of data. That length of data can be sent. And quickly done mathematical operations like filters, DSP applications, major DSP implementation is considered in the FPGAs, because inside FPGAs, as we have seen in the previous lectures, we have DSP block and BRAM blocks as well. So DSP blocks are mostly used for mathematical operations of the filter designs, and those can be operated very quickly, as fast as it can be seen in the results at the output. So some other major applications of FPGA in the advanced fields are image processing, signal processing, data processing applications. So those are the most wide rangely used applications of FPGA as well. So this type of question is very basic, but it can be asked, and it is to test your understanding on the subject. And coming to the next question, how is a for loop in Vhdl or Vlog differ in C programming? It is not the same. In the FPGA development in the Verilog, the only synthesizable loops are if, else, or case statements. The remaining for loop, repeat loop, and while loop are always non-synthesizable, and those are used only to replicate or duplicate the instruction sets, not for the replicating or the repetition of the loops for printing the data n number of times. For loop is not used in Verilog HDL or VHDL in terms of printing the data that many times. Those are only used for replicating or duplicating the instructions. Means to do the set of tasks for n number of times, we are telling okay, for the machine to do this task for number of times, this number of times, by using for loop. But in C programming, for loops are used for printing the data for that number of times, or we can also use that for loop for another set of instructions to be done for that many times of iterations. And it expands the logic in the clock cycle. I mean, by this instruction sets repeated at these many times, and executes all the same clock pulse, and executes all the set of same instructions in one single clock cycle pulse, at one clock pulse. Okay, for loop executed for 1000 times. Okay, 1000 instructions are executed, and all these can be executed at one single clock pulse. So that is the answer. And for the next question, what is SRAM and DRAM? What is the major difference? SRAM is a static RAM, and DRAM is the dynamic RAM. DRAM is mostly used for larger values of data, and here you can see, and also DRAM works fast, and whatever large data transfers that are required, and you can directly use DRAMs for that set of operations in the FPGA designs. Whereas for the SRAM, it is just in the block of memory. If you have a bunch of registers and you have data here and there, and if it is at 0, if it is at 9th position, once you want to write data to the 0th register, and also you want to write at 9th register, you can quickly shift from 0th address location to the 9th address location. So for these kind of quick operations in the memory, you can use SRAM. That is the basic difference of SRAM. These are mainly constructed off the chip, attached to the FPGA, storage of the data. Both are used for storage of the data and processing of the data. Non-sequential data transition between address locations. Like non-sequential is means you can shift from 0 to 6, 6 to 10, and 10 to 4, 4 to 3. You can shift a number of times. And dynamic random access memory is nothing but it is mostly used in the larger data transitions or larger data transmission. Okay, so that is the use of DRAM. You can answer in this way. What is the PLL in the FPGA architecture? Most asked question, guys. PLL is nothing but phase lock loop, and phase lock loop is another circuit device which can be used for generation of clocks. For the generation of clocks. So what is the meaning of generation clocks? You have different modules inside the FPGA design, and those modules are inside the blocks. So in the FPGA entire design, you will have blocks of designs, and in one of the set of blocks, for every single module inside the block, there are the requirements of clock. And for that clocks, some might work at some set of frequencies, and let us say 50 megahertz, and some can work at 100 megahertz, and some can work at 500 megahertz. You never know, but we require different set of clocks, and that clock can be generated using PLL. And how it is generated? In the PLL, we have this clock input given to this and at higher frequencies, and when at the higher frequencies, if we tap this at different locations by the division of the clock, for example, you have a higher frequency clocks, and if you divide it at some particular point, if you divide by 2, you will have for example, in the 500 megahertz clock, imagine this clock period has 500 megahertz of clock, and now it is divided by 2. Now what is your frequency? 250 megahertz of the clock. When I say frequency of operation, FOO, when it is frequency of operation, you should be answering about time period as well. What is the time period? Interviewer might ask, when you are giving an example of frequency of operation, okay, what time period did you consider for that frequency of operation? It is nothing but T is equal to 1 by F. Simply you can do it, guys. So think of this type of calculations that you can do it in the interview room, and don't get too much confused. Be confident in your basic understandings. And incoming clock signals to the spin. I mean, PLL is usually creates the high frequency with incoming clock signals to the spin, and thus generates different clock frequencies. Now by using dividers at the high frequency to generate another set of new clocks. Got it, guys? So this is the understanding of PLL. If you want some more research on PLL, go do it, but it is most important element in the FPGA architecture. And what is inference and instantiation? This is a basic application of FPGA writings. For example, you are writing a Wlog HDL or Vhdl code with some inference. Inference is nothing but it's a generic terminology or generic representation of the module or the design, generic representation of the design that can be wide rangely applied over different EDA vendor tools. For example, if you have been designing in Xilinx Vivado and you have inferred a design, and that design can be easily taken into the other vendor like Intel Quartus Prime tool, and you can work with the same design. Whereas in the instantiation, whatever the designs that you have made in the design, internally the design, that can be used and utilized with a label in the test bench simulations. That is nothing but instantiation. Most of the time we have instantiated the design in the Xilinx or in our EDA playground in the test bench simulation. In the test bench simulation, we instantiate with the module name of the design. Imagine this is a test bench declaration module, and I have mentioned UUT, and inputs outputs should be in the same order. So this is called instantiation. So this is only used in the same vendor EDA tools, where to understand that okay, design and test bench are interrelated, and test bench is simulating the verification for design. So whereas in the instantiation, specific label or format only suits the specific vendor and not compatible to another tools. A simple example. And coming to the next question, what is metastability condition in FPGA? Okay, mostly used. What is metastability condition? Yeah, metastability condition is an error that occurs when you are reading or writing in the same registers, or when you are having a multiple input to the same address locations of the data. So that can be causing a metastability conditions. Like metastability in an FPGA occurs when a flip-flop samples an input signal at a time that is too close to the edge of the clock signal. For example, if you have a clock signal with positive edge, and at the D flip-flop it has samples of an input signal at a time. So most of the samples are relying here at the same edge of the time, and that at that time it has some inconvenience in reading the data. It might mismatch, it might lose some data with more number of inputs at the particular instant of time. At that point of time, due to the flip-flop output, what happens is there occurs a condition called metastability. This can lead to the unpredictable behavior and errors in the stored data due to the input signal being in an uncertain state during the sampling. So when the data is sent in a samples through the flip-flop, when data is sampled like this and all these samples got mixed up at one passage of the clock cycle, that condition gives an unpredictable behavior and errors in the stored data due to the input signal. This is called metastability condition. What is the solution to avoid it? To avoid metastability issues, designers implement synchronization techniques. So after this thing, you should go to that. And synchronization involves clock signals. And for that clock signals, for every clock pulse, okay, this much of samples can be sent through the next module, or this much of data is transmitted in particular amount of clock period. So that is called synchronization techniques using multiple stages of flip-flops. For example, if this sample is in 1D flip-flop, and what if this sample is split into 2 and sent through 2D flip-flops, or if it is sampled with 3 and you can have 3D flip-flops. Now the data is having smaller bits of data here, and that data can be transmitted without any hassle. So that is what involving multiple stages of flip-flops is called. So flip-flop after flip-flop and the other flip-flop is connected. They are connected in a sequence, and data goes in a sequence without any loss of the transmission. Or incorporating proper timing constraints. Constraints like, okay, at particular time of the clock period, this amount of data should be sent. So instead of giving that kind of constraints, you can implement the design, but when you are implementing multiple stages of the design, your design complexity increases. So you have to rely on more number of flip-flops or more number of elements in the combinational and sequential. So that is again a serious issue. There might be some heating issue. And what if this metastability condition prevails? Usually when it occurs, right, at that point of time, you can see the heating issues in the FPGA hardware as well. Okay, so let us go to the next question. What is FIFO? FIFO, we have already done this project, guys. FIFO is nothing but a memory storage element with first in and first out data transmitting device. And it is a first in and first out data transmitting device, whereas whatever the data comes first, that should go first. That should go to the output of the data port at first position. So what comes first goes first. That is the sequence of the transmitting of data. They are commonly used in FPGAs at buffer conditions, at input output buffers, and are made up of registers, block RAM, storing data, and temporarily storing data, and for crossing clock domains. If you have two modules and they are connected internally, and if you keep an FIFO there, you should be keeping FIFO so that there will be synchronization between two different clocks of the modules, such that there will for that cross clocking domain situations, you can, I mean, the data transfers from serial slow to fast and fast to slow kind of data transmission happens from two different module clocks. Then if you keep a FIFO, right, it bears the speed of the data transmission. That is how FIFO is used. What is BRAM? BRAM, we know that we have gone through the class as well in the sessions training. Block RAM is a memory element with 8K, 16K, 32 kilobytes of design in the structure, that deep of the structure, with dynamically sized deep data inputs with specific width designed as per the requirements. For example, you have a VRAM and you can make it into 4 kilobyte, and you can also make it as 32 kilobyte. You can decide what it is like. You have to decide with width, and you have to decide with depth, width and depth of the VRAMs. These can be designed, and major applications of VRAMs are used for FIFOs, dual port memory devices. Dual port memory devices, you have port A and port B, right? You can write and read at the same time, or read and write at the same time. It depends on the different port clocks, different clock ports. Okay, let us go to the next question. Describe UART. And coming to the protocols of the FPGA design, they are mostly applicable at the output of the peripherals, where external peripherals or the devices should be communicating with the FPGA processor. In that case, UART is nothing but Universal Asynchronous Receiver Transmitter Protocol, and that is used for data in and data out, and most wide rangely used for data transmission, that is in and out for the data. And low pin count, UART is having low pin count. It requires only few pin counts. It doesn't require more than 3 or 4 pin counts, and it has only low bandwidth interface, such that UART can be easily operated with low bandwidth interface. It doesn't require more bandwidth of the entire FPGA data transmission. It only utilizes minimum bandwidth, and it is a go-to user protocol. And UART is used for microcontrollers and FPGAs, most widely used to communicate between the FPGA and the microcontrollers, or FPGA and the sensors, or FPGA and some of the servo motors, or any other hardware implementation that you are integrating to the FPGA processor. So that UART is the common protocol that you can integrate it, such that communication happens between the peripherals, between the components and the FPGA chip. So next question is, what is difference between synchronous logic and asynchronous logic? Okay, major difference is synchronous has a clock. Everything, or every process, every data transmission and everything happens with a certain particular point of time with respect to the clock. Everything happens with respect to the clock, every process. But asynchronous, it is not considered with the dependency on the clock. Let us see the answer, how you can give this. The major difference is the clock dependency. In the synchronous logics, registers are used in the communication devices with SPI I2C protocols. So with these protocols, synchronous logic design should be there, like registers. And for the asynchronous, UART protocol is an asynchronous protocol, so that it can shift from different registers or different set of instructions. There is no clock involvement in asynchronous logic. Okay. Yeah, mostly it is, and most of the designs will be synchronous logic. Don't worry, because we are involving most of the sequential elements with clocks, and we do require memory elements in the processing of the FPGA, and hence we do require synchronous logics. Yeah, asynchronous very rarely seen. Now come to the shift registers. What is the usage of shift registers? Only used for converting serial data to parallel input data, and parallel data to serial input data. That conversion happens in the registers, and that is mainly used. What is the main usage of shift registers? Conversion of data from serial to parallel, parallel to data, input data. Okay, then what did you choose, and what is the best language in terms of Vhdl versus Vlog? What do you prefer on your work experience? I do prefer Vlog HDL rather than VHDL, because VHDL, it is more constrained, more complicatedly designed VHDL. So to understand, yeah, many folks of my colleagues are very familiar with VHDL, but I do prefer Verilog. Verilog is also very strong hardware description language, and now the system Verilog is ruling out the VLSI industry, ruling over the VLSI industry. And why do I prefer Verilog? And it is easy to write, and it is very liberal with the syntax that we possess in the description language. And for the Verilog, it is similar to the syntax of C programming. But VHDL, it has its own type of development. VHDL is very old, and now after the developments of VHDL with some good libraries and good algorithms of the EDA tool, people have evolved with Verilog. Most of the European countries use VHDL, and some of the Western countries also use Verilog HDL. So there is a tug of war. Whichever language you learn, it is good to implement with the project-based experience. So good to learn Verilog, then VHDL. So yeah, what should you be considered? What should you be concerned about when cross-clocking domains happen? What is cross-clock domains? Metastability condition occurs when cross-clock domains happen. So if you have a module 1 and module 2, and you have a FIFO between that, if you don't have a FIFO, you have a clock here, clock 1, and you will be having clock 2. There will be no synchronization between two clocks. What happens? Crossing clock domains, the data is crossing between two clock domains. Then at that time, metastability condition is nothing but the data will not be transmitted as it is according to the output port of this and input port of that. At that condition, there will be unpredictable behavior of the entire machine, entire design, between two domains of the different speeds. So this works at slow speed and this works at high speed. There will be a conflict of that. Major concern is about not to lose the data. So that concern is about cross-clocking domains. Crossing clock domains is nothing but at that point of data transmission, you shouldn't lose any data. Create a double flip-flops or creating a FIFO type storage elements will help in eradicating crossing clock domains. As I said earlier, you can create multiple flip-flops, and also you can create a FIFO like this FIFO, and or else you can implement 2 or more D flip-flops, and that will give you some delay, and that will be matching up the frequency from speed to high, low to high and high to low speeds. So this is the solution, guys. This is the solution. Remember, you need to answer this solution as well to give a better understanding of how well you know the subject and how well you have the experience. And coming to the next question, what happens in the place and route? Place and route. After synthesizing the design, after translating the design into the specific logic and specific lookup table or block RAMs or DSP blocks, any other hardware implementation, in the implementation, these blocks should be consuming certain place of the entire FPGA chip, whether they should sit at top of the design, center of the design, and in the bottom of the design, or the right corner, left corners. So you should see these cells to be placed at different set of locations or all these things, right? There will be a floor plan of the blueprint. So based on that, all these cells are placed. For example, clock cells can be placed in the center of the design such that they can be easily connected to any other sequential element, and the clock connections will be easy. For example, you have an FPGA chip and you have a clock in the center such that clock can be easily approachable to any sequential circuit, right? That is how you can design. So this placement of certain cells in the center of the design and placement of some IO buffers are placed in the end of the design such that these are easy to interact between an LCD display. or it is easy to interact with a USB port, or it is easy to interact with a audio jack, right? So that is how IO buffers are placed at the end. So that kind of placement and routing is nothing but connections between the cells, like you have configurable logic blocks and those are connected between the switching models. All these are internally connected after implementation. I mean, after the completion of implementation. In the implementation step itself, you will see the place and route, as I have explained in the day before session. After synthesis, the design implementation stage involves the connections between the internal modules, blocks, placing these in the design. So that is what place and route is mentioned for. In the ASIC design, in the physical design environment, as I am working, in that scenario, you can see these placement of the cells, each logic cell, for example, some of the memory cells, macros, and some standard cells, and how they are connected. All these can be seen at the nanometer scale level at IC stage, and that is way more similar to the FPGA as well, but FPGA is a little bit lesser chip design, but it is on par with the ASIC designs. Okay, so that is the question. And what is the next question? What are the design what are the purpose of synthesis tools? What is the purpose? Sorry, what is the purpose of synthesis tools? What are the purpose of synthesis tools? Synthesis tools are usually available in the EDA environments. Those were given by different vendors. We have vendors like Siemens EDA, Cadence, Mentor Graphics, and Xilinx IDE and Intel FPGA synthesis tools. And for those synthesis tools, what it does, whatever description language you are using, Verilog HDL or VHDL design description, and that description can be converted to the discrete gates or lookup tables and multipliers and block RAMs. So now you have written a block for multiplexer, and this block of multiplexer functionality will be realized in the real-time world into a multiplier design. So that is the main step in the synthesis stage, that whatever description you have made, that can be realized into a hardware device. So that is main use of this description into the discrete gates or lookup tables. For example, you are writing a memory, right? And if you are having a only read-only memory, right, that BRAM design can be realized to only lookup tables. Got it? So that is what it looks like. That is synthesis tools. And we have another question called what is SerDes in FPGA? This can be asked if you have been applying with some experience. SerDes is nothing but serializer deserializer. Serializer deserializer is a high speed way of sending data to the low pin count interface. For example, you have 64 bits of data, and that 64 bits of data should be sent to only 4 pin. Then how it is sent through it? We have a SerDes in FPGA, that kind of hardware implementation which has low pin count and which requires 64 bits of data to be sent through the low pin count, and it is commonly used for PCI Express. Nowadays PCI controllers, one example is Ethernet port. In your PC, if you can open the Ethernet device that is attached to the motherboard, if you can see the device, that is nothing but a PCIe controller, PCI Express controller, and that has very low pins, but it can have the larger number of data transmissions, not the Ethernet hardware, some other PCIe implement. And SATA cable is mostly implemented in terms of our external hard disk. We have a wire that is having very less number of pins, but we transfer the data in terms of gigabytes, how we are transmitting. So that is another application of SerDes. So consider your FPGA is like your external hard disk. You have written a greater memory design on the FPGA and implemented, and for that FPGA you want to process the data you read and write with small cable, with small USB cable, with very low pins. What happens? You need a SerDes application in that, and one another gigabyte Ethernet or high speed video applications on the FPGA. For those kind of things, in high speed video application is nothing but your FPGA has a VGA port, right? So whatever data you have in this memory block, you have a huge number of data, and this is DRAM, 8 megabit DRAM. This is internally connected, and these connected FPGAs will be connected to the VGA port. Whatever memory you have on the video format, that is sent through the FPGA and it is connected to the VGA port, and you can attach a display. But VGA port has hardly 12 pins, 16 pins. It depends on that thing. So that is nothing but it has a SerDes, serializer, deserializer. I mean serializer and deserializer. Something implementation in horizontal and parallel representations in the levels of data. So that is one set of interview questions that you can get, and if you have been answering some of them, very good to know that. And if you have stuck at some of the things that you don't know, it is good to research on your skills and get more understanding of the FPGA and go to the better reading of the data. I mean, get a good knowledge on hands-on experience of the FPGA development. And if you have any further questions, please let me know. I'm here to help you. Thank you.